Well, we can generally hear you. Just try to stay close to the computer. Yeah.
1, 2, 3.
Yeah, we can hear you.
Okay, so I will try to stay
Working great.
here. Yes, it's difficult for me to see the presentation. Yes, so we introduced the model. It is up to now it's abstract, so we know abstractly what could be the state of quantum system. This is a vector in a high-dimensional linear complex space. So we know quantum gates. Theoretically, it is unitary operators of these spaces, and we know measurement, which is a bit vague thing. Yes, it's more complicated story. It is probabilistic. It doesn't have analog in classical world. Yes, so this lecture, yes, I would like a bit to settle us down. Yes, so to demonstrate how to do something inside this model, and start to land us on the physical devices. Yes, because in the end, yes, still there are some elementary operations which are possible. Yes, and I will start to combine from elementary operations more difficult operations. Yes, but before, yes, let us, as promised, let us speak a bit about the exercises which were done for home. Yes. So did some of you looked on the block sphere examples? Do you know where if it is the point on the block sphere, what is not of it?
It flips point.
What means flips?
It is reflection that is displaying the
Yes.
equator. It's reflection.
Reflection from equator.
Yes.
Yes. So if it is reflection from equator, yes.
Yes, it will be like consider the diameter, it will be on the other point.
So diameter means so if it is such point, it would be where? Here?
Yeah.
Kind of via the center.
Yes.
Via the center. Okay, so there are two different answers. Might be some of you have a motivation.
Yes. Yes. So the reflection is vector diameter, this vector line.
Of horizontal diameter.
Yes, the green line.
The reflection, so three possibilities. So, okay, so then let's have a discussion. Who would like to say arguments?
Oh, okay, but when I said around the equator, it turns out that I meant exactly the same.
Okay.
Okay, but I meant
with respect to
the line.
With respect to line.
Okay.
Or to the plane. Yes, so Altan thinks that it is with respect to line. You think that it is with respect to equator. And you think that it is with respect to point. Yes? So, okay, then how we can get a solution for it? Yes? So, first of all, yes, 0 and 1 goes into each other under all of those three conditions. Yes, so, okay, let us see some point which is different for those three conditions. Yes? And for example, I think the point which is different is 0 plus I1. Yes? So this is that point.
It doesn't belong to the sphere.
Correct. Thank you very much. 1 over square root of 2. Yes? So thank you very much. Yes, so I meant this point. Yes, because with respect to equator, it is fixed. No, it is would be the same for center and for green line. So it would be the same. So let us find another point.
What is 0 and 1?
Well, let us start with this one.
What is 0 and 1?
What?
A0 and A1.
This is two complex numbers.
Just two complex numbers.
This is just two complex numbers, such that the sum of their squares is 1.
We point on CP1.
Yes, but we interpreted it on C2. For us, it's much more important linear structure rather than projective structure there. Yes. So for us, it's important to have linear. So there was a reason why I made this easy mistake. Yes, when I forgot to put 1 over square root of 2. Yes, because I have much more interpretation of this. Yes.
And this is bar and right bracket reflection.
So this is the basis vectors. This space. This is the notation which we use.
For the first vector, you see it's squared, and the second vector is squared.
Yeah, but this is logically means 0 value of cubic and the cubic has value 1. So here, just I kind of insist to use my language, not immediately go to algebraic, things, varieties which goes there, because it's very nice to define things there, but this is not how computer works. Yeah, okay, it works like this, yes, inside, yes, but this is not how to understand work of algorithms. Yes, so we have a point. Let us see what would be its image.
I have to update my answer.
Will you change your answer?
I will update it actually. If I write in the spherical coordinates, actually the point, then this should be just changing the z coordinate of the. Okay, then this goes to sine of phi, cosine of theta, then cosine of phi, cosine of phi, cosine of theta, and then cosine of theta.
Okay, let us continue this example.
Okay.
Yes, let us continue. Now, what is theta here? Let us once again to practice. Yes.
Is pi over 2.
Pi 19.
So it's pi over 2. Yes.
We're considering just like the first round. Like we're considering like pi over 2 plus 2 pi times
So
8.
for us, theta is something which lies in interval from 0 to pi. Yes. Yes, because cosinus of theta divided by 2 should be equal to 1 over square root of 2. So theta, so it's cosinus of p over 4. So theta is p over 2, yes. The point is on the equator. Yes. So if the point is on the equator, then okay, the next, what is phi? Well, so everything is real. Yeah, so there's we have gamma equal to 0. We can take phi equal to 0. Oh, there should be 0 plus 1. So it's not equal. There's a mistake. Yes. 0 here is 1. I forgot to correct. This mistake.
What is it? Theta is different?
No, it's forgotten to put here 0. Yes. And it's forgotten to put here 1.
So I take cosine theta divided by 2 0 and sine theta divided by 2 1.
Sorry for the mistake. Yes, and okay, what is phi? What is phi? Yes?
Is it pi over 2?
It's not real. Yes, it's yes. So e to the power I phi should be equal to I. Yes. Okay. Pi phi equal to pi corresponds to -1. Yes. So this is pi over 2. Yes. Phi is equal to pi over 2. Okay. So if you consider not this, yes, it would be 1 over square root of 2 I0 plus 1. So what would be there? The pipe side there. Correct.
But getting 0 means still with 0 state, or it's now with the 1 state?
But now this is state. Yes, so this is state. Yes, not of side. Not side. Let's go to this. E. And now, what would be theta for it? Okay, let us represent in this form. And so we need to put I in front. Because we want to have the first part to be real. Yes. So this becomes 1 over square root of 0. Now minus I. Minus 1 square root of 2 I 1.
You say real, you say first part real, 1 is your first part.
No, that's what stays in front of 0.
Ah.
Yes. So theta is once again, so gamma we don't care. Theta is once again p over 2. Yes, and now we need to find phi such that e to the power I phi will be equal to minus, because it has minus. Yes, so phi would be equal to 3 pi. Yes. So this becomes an opposite. Yes, so equator. Finish, but you finished yourself. Yes, so but those two options are still in the business. Yes. So okay.
Actually, along the line, maybe not, not this one, but so we're talking about one.
Which of the problem?
The result line, which passes through the point that you wrote 0 plus I.
No, it's definitely not it. As for green line, it still works. That's because this point goes to opposite. Goes from here to there. Yes. So for green line, it still works. That's okay. So now, okay, well, what are our expectations? What point to consider now?
Is this picture the when you help? I don't understand how you are writing as S2 unitary experience C squared. Unitary experience C squared is three-dimensional.
Because we also have equivalence.
Ah,
So we have equivalence of all vectors which are multiplied by a complex number.
okay, yes.
So we have more relations there than just C. Yes. So this point.
Yeah.
Yes, if we consider this point, yes, its reflection via center would be here, and the reflection via green line would be the same. So what is this point? Let us solve an opposite point. So this is theta equal to pi over 2, equator, and phi equal to 0. Yes. So, the value is, yes,
0.
Sine.
so this both comes to 1 over square root of 2, yes, and e to the power I0 is 1. Yes, not of psi is psi. Yes, so it stays the same. So the equator doesn't work. Yes, so the works, the only thing which works is my yours.
I have a computation. I can show.
What?
I have tried to compute for general case, not for particular ones.
Yes. So,
Everything's probably wrong, so you have to correct it.
okay. I have never against such things.
Hey, right?
Erase, yes. Erase and try to speak louder.
I'll be writing and you'll be speaking, okay?
Okay, that's fine.
So first of all, what is it? I have what's that? 6 over 2, then 0 plus e to the I5 sine 6 over 2, 1, and then where does it? So this is my state, and I'm applying to it my transformation. So I want to write
Both side.
side. Sorry.
Not to confuse it.
Now I want to express psi, which is a state, and what are its coordinates? The coordinates are by definition e to the I5 of the sine of theta over 2, 0 plus cosine of 5 over 2 times 1. So I just flipped the two coordinates. Now, first, thank you so much.
Theta, yes. So here is theta, here is fine.
Now we want to apply the equivalence relation to make the first first coefficient real. Right here we have a complex number, so let's multiply everything by the inverse square. So instead, I should write sine theta over 2 times 0 plus e to the minus I5 times the cosine of theta over 2 times 1. Right? But we want to get another thing. We want to get the cosine, some angle. So which would be the angle cosine of this angle? I don't know how to call it. Let's call it theta prime. It's the different one. So I need theta prime such that the cosine of theta prime equals to the sine of theta. Right? Then
So write something each.
e to the I5 prime times the sine of theta prime over 2 times 1. So we want to solve this.
Yeah, I think the first one's 0. Oh.
Thank you so much, guys. You're helping me a lot. Now, what would be theta prime is equal to what, and phi prime is equal to what? How to solve it? What is the angle such that the cosine of this angle is equal to the sine of another angle? So if I'm not mistaken, we just should rotate everything by pi over 2. So if my angle is 90 degrees rotation, right? But which direction? So what I'm claiming is that the cosine, if this was my angle theta, right? Then sine is here. This is sine of theta. Now it is equal to the cosine of this angle, which is theta plus pi over 2. So what I'm claiming is that this is equal to theta plus pi over 2.
I would say that
That's an
it
option.
should be pi over 2 minus theta. You should not rotate, you should make a symmetry with respect to x equals to y. You should make a symmetry with respect to the x equals to y.
Well,
Because for now your sinus theta becomes
No.
minus cos. Sorry.
what I'm saying is that the cosine of this angle equals to the sine of theta.
Can you write?
No,
This implies that cosine, or not implies, it is implied by the fact that cosine of theta plus pi over 2 equals to the sine of theta, which we illustrate in this picture, which everyone.
So, which is not correct. That's like so I remember from my high school time.
Thank you so much.
Yes, I remember from my high school time that cosinus of pi over 2 minus theta is equals to sinus theta. That I will prefer to write here.
But these two things are good, aren't they?
No.
Why?
Because sinus of minus theta is equal to minus. This is plus and here is minus. This is,
Yeah, for sure. But
Please join the discussion, please.
Yeah, I think the problem with summing pi over 2 is also that you could go over the limit, right, of
And
pi
also,
of theta.
if you consider theta equal pi, it will go over the limit of theta.
Yeah,
Well, what I see is that you have the sinus theta and then you're having minus cosinus theta equals to sinus theta in this picture. That this picture actually shows that theta plus pi divided by 2 is not a correct answer. It should be p divided by 2 minus t minus 2. Because it's a symmetry with respect to the axis.
No, so first of all, yes, so let us substitute like theta equal to 0 would work. Yes. But let us substitute what? Let us substitute pi.
Which works. I mean, it shows that the formulas are correct.
So if you can
you're right. Thanks.
Cosine of pi is sine of 1.
Indeed, thank you so much. So it's apparently I don't remember basic economics. Thanks. And yeah, I guess your suggestion is it might be better.
by the way, sinus is projection on y coordinate, sinus is projection on x coordinate.
Is it?
Yes.
Ah, that's good. I think this is great there. Great. Pi over 2 minus theta is my option. Does it work or not?
I can divide by 2. Yes.
Fine, like this.
Yes.
Does it work better? Because now, if I substitute this, then here I would have the cosine of. So this works because the cosine of pi minus theta over 2 equals to the sine of theta over 2. Is it true? Well, I guess so. Now, if we use such substitution, then what would be the phi prime? Let's take a look at the second coordinate. So, what is the equality that we want to check? We want e to the I phi prime times the sine of what? Of the theta prime over 2, which we can substitute now as pi minus theta over 2, and that whole thing is equal to e to the minus I pi times the cosine of theta over 2. Now, what is the sine of pi over 2 minus this? Well, I guess it's probably the cosine of theta over 2. Is it the case?
Yes.
Thank you so much. Now these two cosines cancel out, and basically we have the exponent of I phi prime is equal to the exponent of minus I phi prime. This yields minus 5. And now that would be my substitution. This is the thing which happens under this knot transformation. When I use knot, what happens is that this point, this point, right?
Yes.
This point, which has the angle phi and the other angle theta, it is being mapped according to this formula. So phi negates, it used to be here, now it's reflected with respect to this vertical plane. I'm not sure if you can follow, maybe it's better if I draw, but basically this goes to there, but we also have to reflect with respect to the angle here. So my angle used to be theta, now it gets to be pi minus theta. So it goes the other direction. This angle becomes this angle. It is reflected with respect to the horizontal line, and I guess that's.
No, it's still on the upper part. It's still above the equator.
I'm not sure.
It applies and is reflected.
To pi minus theta. So let us see, like, okay, yeah, thank you. That's actually much more.
Yes.
So geometrical interpretation is not so much important. I told that block sphere is used just to visualization of the value of qubit. It's not very important for actual calculations. Yes. So important is this. Yes, but okay, still geometrically. The first one, so if you look here, it means that you reflect with respect to equator, with respect to two-dimensional plane, and this is either rotation over vertical line, yes, this is rotation over vertical line. No?
It's reflection with respect to vertical plane, rather, because it's minus. Pi goes to minus.
Yes, not yes. Yes. So it's reflection with respect to vertical plane or the plane of the blackboard. Composition of two reflections is a rotation with respect to the intersection of those two, which is this green line. Rotation by an angle 2 times angle between the planes. Rotation by 100 by pi. Yes, and the rotation by pi is okay. No, this is rotation by pi. This is not the reflection.
This is symmetry with respect to a line.
Is it symmetry with respect to line, or it is rotation?
It's equivalent. Symmetry with respect to line is the same as rotate by
Over the line. Yes, correct. Yes.
I was right.
Yes.
It's by my technical calculus.
Yes. Okay. So let's not do now the second, yes, because we are going to spend some time. I still want to speak some lecture today, yes. But you are very welcome to send me your solutions or your answers, or to have a discussion with chat. In chat, I will moderate it. Yes. So let's go. Measurement part. So I will actually never in this course, so only on this extra exercise section, discuss the measurement with respect to arbitrary operators and when you can change order of them. Yes, I will not discuss this in the class. But what I really want to discuss. So, by the way, so the Zoom still hears me because I went left. Good. Yeah. So the measurement of the qubit. Yes. So that's if I can measure first qubit after this measure, second qubit, I would have the same result if you can measure second qubit and after this measure first qubit. And this I would like to explain why it is like this. Yes. So assume that we were in a state more than 2 qubits, but still we can represent it in the form first 2 qubits, some coefficient, first 2 qubits 0, 0, some other state, B 0, 1, other states from this form. Okay, so we just kind of separate the first qubits, but we track what are the coefficients in front of that. Yes? And what would be the result of measuring of the first qubit? Yes? I need actually to represent it even in more. Yes? I should write it 0. Yes, and it would be times A 0 psi 0 0 plus B 1 psi 0 1 plus 1 over C 0 psi 1 0 plus D 1 psi 1 1. Yes?
Okay, and then
No. This is not a state.
Yeah.
Yes, because A squared plus B squared is not equal to 1. Yes? So I need to write it in the form that this is A squared plus B squared times 0, A over A squared plus B squared, square root, square root, yes, plus B over square root of A squared plus B squared. Yes. Yes, and plus a similar term 1. Yes. And note, yes, that now for this, the sum of here coefficients, sum of square, then is equal to 1. And 0 sine, so 0 sine 0, 0. So I have a lot of measurements. Yes, and plus 1 sine 0, 1. Yes. And okay, yes. So what would happen? Yes, in the first measure. So this probability square of this term, we will get 0. Probability A squared plus B squared. And by the way, it's like for future, yes, this probability is easy to calculate. So you look all the terms which start from 0, yes, and you calculate square what is in front of that. Yes, so A squared plus B squared, you get 0. C squared plus D squared, you get 1. Yes, what would be the state? Yes, it would be 1 over square root A squared B squared of what is happening here. So if we got 0, we change the state to this one. Yes. And now, what happens if after this, so assume that we go to the 0. What would happen if we measure now the second? Yes. And if you measure the second qubit, so to get 0, we look only onto this term. To get 1, we look only onto this term. So to get 0, we will have A squared over A squared plus B squared. So, and in that case, in order to get 2 zeros, we need first time to get 0 here, which happens with probability A squared plus B squared. And the second 0, which happens with probability A squared divided by the previous. So those measurements are independent. And this is actually what I forgot to state in the previous lecture. So as soon as you make certain measurements, all the next measurements independent with the result. Yes? And in that case, the probability to get two zeros is the product of those two probabilities, which is equal to a squared. Yes, and what is nice, this is exactly square of the term which is in front of it. Yes? And I mean, I can make, theoretically, I should make focal computations to reach probability to get, if I measure first and after second, and four calculations to get, if I measure second and after this first. But because the answer is so simple that this is square of coefficient in front of this term, that it doesn't depend on the order of how I measure. The final state would be 0, 0, psi 0, 0. So it would be exactly the state which is there. So the general idea is that you should represent whatever qubits you measure. Yes? You should represent it in such form, and the answer is here. So you get square of coefficient, the probability to get this sequence of answers, and you would put yourself in a state 0, 0, psi 0. Yes. So this is what is happening. Yes. And this is the reason why I can say the phrases. I would not specify in which order I measure. Or I can say phrase, let us measure first two qubits. Yes, because it doesn't matter. In which order, the result is the same. And this is what would be useful in the course. Okay, so I finished with the review of the previous lectures. So I come to new material. Let's have a pause, I guess. Might be I will be managed to resolve the issue with microphones. So 5 minutes break.
Eu acho que se pudesse seguir essa linha, eu
I don't know actually how it's supposed to work. Yes. Usually I ask from Carlos to get it.
Por exemplo, eu acho que o bicho, por exemplo, às vezes 0 vezes 0 vezes pi alguma coisa. Isso parece ser
Isso.
É base, eu fiz 0 e
Isso é seu, certo?
No, this is for this one.
Ah, ok.
This I have no ideas what it is. I should turn this also on. This looks. Yes, and now they are both green at least. So that's not so easy to resume. Okay, where is Lada? She's coming. Yes. So now the first algorithm which I would like to present. It still would be an artificial algorithm. So this is not what you will, use in real life. But this is the algorithm which I like because it shows, what is happening inside quantum computer
even that we don't learn a lot of operations which we can do there. So the setup of the problem, yes? So assume that we have a function which from numbers from 0 to 2 to the power n minus 1, so from n of sequences of length n of 0 and 1, tell you true or false, yes? Tell you 0 or 1, yes? Basically, this is a typical, combinatorial problem, yes? Whatever it is, yes? So usually you ask, is it, this system satisfy your conditions, yes? And this well fits to those who knows P and P problems, yes, because this is the way to verify if something is a solution, yes? That's that kind of. Is the schedule of classes good? Yes, it checks, oh, every teacher is only in one class at the same time, every student is only on the one class at the same time. It's much easier than just to construct a function. Yes, so we know this function, yes, and assume that we also somehow a priori, yes, so that knows that this function is the constant, yes, so all the values are the same, all the outputs are the same, or balanced. So for half of the inputs, it will give output 0, and for half of the inputs, it gives 1. Yes, but we don't know is it constant or balanced. Yes, and we don't know in which states it is 0 and which states it is 1. Yes, but we a priori know this, and we want to understand is it constant or balanced. So those two cases. And this is a specifically created problem. Yes, it just well fits quantum computing. And before I show the BLESS, so how very quickly quantum computer can answer to this question, I will show the curse part. Yes. So, but what does it mean for quantum computer to have function f given?
Sergey,
Yeah.
can you quickly repeat the question? I missed it. Sorry.
Or what? So what means that the function f is given? Yes. And because for in genuine just functions, so in computers, this means that you have an algorithm how to calculate it. Yes. But for quantum computer, the only operations which are allowed should be linear. So it's not function which goes from a set of n0 and 1 to 0 and 1. Yes, it should be linear operator. Yes, and it should be unitary. Yes, so in any case, this is not a proper linear operator because it's not reversible, it's not from the space into itself. And there is an answer to this question, which makes kind of telling what is this function much more complicated story. Yes, so we say that we know the function f if we have operator uf, which would act moreover not on n qubits, it would act on n plus 1 qubits. So we have n kind of responsible for input and 1 responsible for output, basically. Yes, and it would be acting, so I will not define how it acts in general. I will define how this operator acts on basis vectors. And because it is linear operator, if I know how it acts on basis vectors, I know all the action. Yes, and I would say, so if x is sequence of 0 and 1, so number from here, and y is just 0 or 1, then it acts on such system of qubits. So this is n qubits, this is 1 qubit, in a such way, so it doesn't touch the first n qubits. So it keeps it as it is. The input stays input. Yes. And the output, you cannot say set up at 0 or 1, yes, because in that case it becomes not reversible. But you can summate y and f of x modulus 2, yes? In such summation, I would denote by such a symbol, yes? So kind of, if f of x is 0, then I don't change y. And if f of x is 1, I change it, yes? I apply not to it, yes? So when this becomes an operator, yes, because it also sends basis vectors to basis vectors, yes, and it is reversible, yes, because you can calculate back, because you look here, and actually its square is identity, yes, and so this would generate a unitary operator. And when I say that I know the function f, and it would be not the only moment in the course where I use something like this, I would mean such kind of things, yes? The official name of this operator UF is quantum oracle, yes? So that's, the oracle is a person who you can ask, you know, for inspiration of future, yes? And it is asked like this. And when I say that f is given in computational, in quantum computing terms, this means that I have a program which implements UF. It could be whatever. Yes, I might. I mean, in this lecture I will use it as a black box, so I will not kind of refer to more details. Yes, and this is the story that what is function to be given, because I mean we still want to operate with notions from our world, which is in our mind. Our mind has logic. Yes, it's from 0 and 1. Yeah, this is computer logic, or computer has logic because we have this one. Yes, so who knows? Yes, so this is the state. Yes. Now I would like to show an algorithm how it, like, which would implement. So how by UF we would determine is the function f balanced or constant. Note that, like, first I will show for 1 qubit. I mean, nonsense. Yes, it's very easy problem. But I mean, un poco, step by step. Yes. So note that whatever, if we consider for 1 qubit, whatever is f, it is either balanced or constant. Yes, because it's just from 0, 1 gives you 0, 1. So it's not so many such functions. Yes, and this is the scheme which would do this. So we consider the qubit, yes, so on which is input of f. We consider this n plus 1's qubit, yes, which I called Atzilla. I don't know why I put n here. It is Atzilla qubit, yes. And so which is kind of an additional qubit that we needed just to define UF. And this is the scheme which would answer to our question. So first, we apply not to Atzilla qubit, yes, to Atzilla qubit. After this, we apply Adamar gate. Yes, recall the Adamar. Yes. So which sends 0 to 0 plus 1 normalized. Yes, normalized 0 plus 1. Yes, and 1 to normalized 0 minus 1. Yes. And after this, we do the quantum oracle. And after this, we do once again Adamar on the first qubit and measure it. And by result of measurement, we will, a result of measurement is either 0 or 1. And by this result, we say, is it constant or balanced. Yes. And so I will do straightforward calculations on the next slides. Yes, and there would be three critical moments. Yes, so one just before apply quantum oracle, just after application of quantum oracle, and one more Adamar gate. And in the end, there would be measurement. Okay, we will do it, but it would be obvious. So let us see what would be in the state one. Yes, we start from 0, 0. We apply not to it, so not to a second. So we will get 0, 1. After this, we apply to both of them Adamar. Yes, and 0 would be mapped to 0 plus 1 normalized, and 1 would be mapped to 0 minus 1 normalized. Yes. And okay, I will write it, so I can multiply those two numbers. This is 1/2 of sum minus. Yes. Don't remember, you cannot open bracket that sum plus minus is the first squared minus the second squared. So that when if you open bracket, it is 4 vectors. Yes. And okay, now before I come to a calculation of the UF by itself, let me consider how this operator acts on such a vector. And here there is one important thing. So I abuse notation a bit because a quantum state is only consists of unitary vector. And this is not a unitary vector. Yes, because its norm is equal to 1 over, it's equal to square root of 2. Yes, it's not normalized. But because UF is linear operator, I still can apply it as a linear operator to arbitrary vector. Yes. So then, and I will do this a lot in the course. Yes. So just, you should be very careful kind of where you have a state, where you don't have a, like where you are normalized, where you are not normalized. Yes. So this is not normalized. But still, you know how works UF, yes? If f of x is a basis state, Yes, if f of x is equal to 0, then x0 would be moved on to x0, x1 moved to x1, so x0 minus 1 would be moved to x0 minus 1. Yes, and if f of x is equal to 1, x0 would be mapped to x1, x1 to x0, and x0 minus 1 would be mapped to x1 minus 0. Yes, so minus x0 minus 1. Yes, and I can write it in general form. I can write it like this. Yes. And this is where I would use kind of magic of mathematics. Yes, because yes, this is a formula. It's a correct formula. Yes, while its proof is completely logical. Yes, it's not linear proof. Yes, it's logic. I consider two cases and just realize that this formula is correct. Yes, so and so on. Yes, but I will do such trick a lot of in the course. Yes, where you kind of, because this is the idea, the mind is still logical. You will create a logical statement, write it as a statement for linear spaces, and after this manipulate with linear spaces as you manipulate with linear spaces. Yes, so this is the typical story what you do in quantum computing. Remember, those who are smart can say that, oh, but those guys are equal. Yes, but no. We will not have only basis state. Yes, we will have sum 0 plus 1. Yes, so if you erase minus here, then you cannot plug in it in linear calculations anymore. Yes, so this is the story. So because of this, I did not erase here minus. Because of this, I still have this form. And let us remember it. Yes, and by the way, yes, even that I considered it's only for x1 qubit up to now, it actually can be done for n qubits. Yes, even if you go to n qubits, this formula is still correct because all of those calculations are correct because I never changed x. Yes, I was needed only value of f of x. So I don't mind is it a 1 qubit or multiple qubits. So remember this formula. Yes, so okay. Now I want to go from 1 to 2. Yeah, so this was a state for 1. 1/2 of a sum of 0, 1 times 0 minus 1. And now, because I know that if I apply UF, 0 times this part will go to minus 1 to power f of 0. 0 plus minus 1 of f of 1. Yeah, so I separately look onto this state and onto this state. And I apply the result of previous slide. Yes, and this is how it would work. Yes, so I still have 0 minus 1 on a second qubit. Yes, and in the first qubit, I just put multiplier minus 1 to the power f of it in front. So this is what has happened. Yes. And this is a certain magic story, yes, because I started with a direct product. I applied certain gate which has manipulated with all of them and still get a direct product. This is not always the case. Just so this is a special story because I put the second qubit in a state 0 minus 1, and kind of this was a specifics. It's not always like this. Yeah, so it's very rare that if I started with direct product, apply 2 qubit operation, I will get in the end direct product state. It's very rare story, but here I get. And because of this, when I would calculate this second atomar, I can just concentrate on the first qubit. Yes. So if f of 0 is equal to f of 1, yes, then those terms, those terms are equal, and I can put multiplier in front. Yes, and so this is the value. So by Adamar, it would be put it into 0, might be this coefficient plus or minus 1. If they're not equal, but if they're not equal, then minus 1 to f of 0 is equal to minus 1 to f of 1. Yes, and so I would have a multiplier minus 1 to the power f of 0, and here we have minus. And when I apply Adamar to 0, 1, to 0 minus 1, I will get 1 here. Yes, so if f of 0 is equal to f of 1, that at this moment I would have here some coefficient times 0, plus minus 0. And if they were not equal, then I will get here plus minus 1. Yes? We consider special case n equal to 1. Yes, 1 qubit. Yes, so because of this, there is only 2 values, f of 0 and f of 1. Yes, so this is a simplified story. Yes, and in that case, we get either 0 or 1 as a result. And okay, so this is the final state. So if you, here should be minus. I put too many misprints in the presentation. Yes. So this is minus. And then I mean, if I measure, then if I get 0, so I was in this situation, so the function was constant. And if I get 1, then they were not equal, so the function is balanced. Okay, yes, but this is for one qubit. This is not a superstar. What would be for general case, for all n, for the case of n qubits? In that case, this is the scheme which would solve it. Yes, so I would consider n qubits. I would apply Adamar to all of them. I will consider ancilla qubit. I apply NOT and Adamar. After this, I apply quantum oracle to all of them. Yes, and after this, apply Adamar once again to the starting qubits and measure all of them. Yes, so not one, but all of them. And after this, depending on the result of measurement, it would be all 0 or 1. I will be able to say by classical logic, yes, it was the function balanced or constant. Yes. So, but the calculations I will show on the next slides. Yes, so this is the scheme. Please, perguntas, dúvidas, provocations. Okay, so let us do calculations. I will have the same 3 critical steps, but of course the calculations will be harder. And I hope they will have less misprints. So if we got 0, then the function is constant. If we get 1, then the function is balanced. But yes, this is exactly the story. That quantum computer is supposed to be probabilistic, but it happens that in any case, it would end up that, first of all, the result would be a product state. And the second, the first qubit would be either in state 0 or in state 1. It would be no mixed state. It would be no superposition there, yes? If the function was balanced, if the function was constant, yes, then the first qubit would be in a state 0 without superposition. If the function was in balanced state, then the function would be, then the first qubit would be in state 1, yes? And the measurement would be deterministic. By the way, for case n, it would not be completely like this. Yes? And for the case n, the final measurement would be still probabilistic. So we would be able to get the answer, I mean, with certainty 100%, yes, so with full certainty, but the measurement by itself would be probabilistic. Yes, but here it is not. So if the function was constant, we will always get output 0. If the function was balanced, we will always get the output 1. Yes, so this is the good duvida. Yes, good. This is might be confusing. Yes, this is the story. Yes, so in most of algorithms it would be like this, but here it is special algorithm which would work exactly. Yes, so this is a very special. Yes, so we have this story, and now we need to do the same calculation. And I mean, they are much more difficult. Yes, because now we don't have 1 qubit, we don't have 2 qubits, so we can write everything exactly. We have n qubits, so we should use dots or sums, yes, somewhere, yes. So, but first step, yes, so when we come to the 1, yes, the first n qubits, we just apply Adamar to them. So we get 0 plus 1 normalized. And here in those calculations, I would be very careful calculating this coefficient because it allows to simplify the calculations in the end. Yeah, so because each of them has a coefficient 1 over square root of 2, so the total coefficient here would be 1 over 2 to the power n divided by 2. Yes. And the last qubit, Atzilla qubit, I first apply not, and after this Adamar, so it would be 1 over square root of 2, 0 minus 1. And now, if we look onto all these brackets and open all those brackets, yes, we will get so we will get 2 to the power n terms, yes, and in each of the term, we would have a sequence of 0 and 1. And as I was suggested notation, yes, so I will associate sequence of 0 and 1 just with integer number, yes. And so this is the sum. This is the opening of those brackets. Yes, so this way is just opening of those brackets. Yes, and okay, I don't touch the second term. Now, yes, I'm starting already to go from 1 to 2. Yes, but the reason similar to 1 qubit case. Yes, if I consider such state, yes, yeah, and by the way, yes, here, so here is sum of k and sum of squares of coefficients, yes, would be 2 to the power n, and square of this is 2 to the power n, so sum of the squares of coefficients would be 1. Yes, so this is, I mean, this is not, I didn't cheat you. Yes, so this is a correct calculation. In particular, it gives the coefficient, the norm 1 of this. Yes, but okay, if I consider such a state, and by the way, this is a state. Yes, so because its norm is equal to 1. Yes, and if I apply U of f to it, I will get this result. Yes, so I will just put multiplier of minus 1 to the power f of k in front of it. Yes. And so if I would apply this wonderful formula to this expression. Yes. So then at moment 2, yes, I will have state that I just put coefficient minus 1 to the power f of k in front of each summand. Yes, so it's each element. And now, okay, this is a direct product state in terms of first n qubits and the last qubit, but this itself, yes, it's not a direct product state. Yes, so we even don't know it well because it uses function f. Yes, and so now comes the most difficult part of the calculation. So we need to go from 2 to 3. So we need to apply Adamars, yes, to this sum as it is. So yes, it is the same as independent. Yes. So the first n qubits are independent from the last one, but among themselves, n qubits are dependent. Yes, are potentially dependent. Let me have like this. Yes, and okay, now we need to calculate to this n qubits, to this sum, the Adamar gate to each of them. Let me start with an exercise. Yes, let me consider 1k, which is a sequence of 0 and 1. So k1, k2, kn. Yes, and apply Adamar gates to it. Yes, because it happens the following. So I would independently to each 0 or 1 apply Adamar. And Adamar for 0 gives you 0 plus 1 with coefficient. Yes, and for 1, it will give 0 minus 1. So I can summarize this in such form. Yes, and I don't know why I didn't put it on the slide, but I just can say that h of k is equal 1 over square root of 2, 0 plus minus 1 to the power k. K1, 1. Yes? So this, it works like this. It is a correct formula. Yes? And in that case, I can write it in such form. And now I can open brackets once again. And I don't like, for each sequence of 0 and 1, I would have certain coefficient in front of it. Yes? But the one thing in which I could be sure that the coefficient in front of all zeros is equal to 1, because here, everywhere, 0 was with coefficient 1. Yes? And I will write it in a such form. So I kind of, up to now, don't care. You theoretically can write exact formula. Yes? It would be plus or minus 1, yes, and you can calculate in which power, but it doesn't matter for future. It matters that the coefficient in front of zeros is 1. This is what is important. Because now I will substitute it here. Yes. So because I can apply Adamars to each elements independently, and after this summate them back. Yes, so I have 1 over 2 to the power n over 2 in front here. I have minus 1 to the power f of k here, and I have this expression inside. Yes. And up to now, only thing which I will do is just two constants, which were the same. I would just multiply them. I would put 1 over 2 to the power n. Yes, and it's a nightmare. I have a sum, and inside it I have a sum, a very complicated expression. Yes. But let me concentrate what would be the coefficient in front of all zeros. Because if f is constant, then minus 1 to the power f is also constant. So this coefficient would be the same everywhere. There is exactly 2 to the power n terms here. So and each of them would have the same. Yes, and I have a multiplier here. So I will get coefficient 1 here. And plus something else. Yes. But now comes interesting statement that the norm of the vector should be 1. And I have here element with coefficient 1. And here I don't have 0 inside. Yes, because everywhere z was starting from 1. So all of those elements are orthogonal to this one. And this one has length 1. And the total vector has length 1. So this is, all of this is 0 in the end. So if the f was in a constant state, yes, was constant, then in the end, I will get all zeros. Yes. Imagine the kind of, it's the same as assume that uf didn't do anything. Yes, then just Adamar plus Adamar gives you change nothing. Yes, so that's, so you will get 0, okay, might be with coefficient minus 1. Yes. If in opposite it was balanced, yes, f was balanced, then I would write the same. I look on the coefficient in front of 0, and this would be sum of minus 1 to the power f of k. And half of them would be plus 1, and half of them would be minus 1. So this sum would be 0. So I would not have any, I would not have this term presented in my sum. Yes, so I would have only the last terms. Yes, and finally, so if the f was constant, that result of measurement would be necessary 0 with probability 1. Yes, with probability 100%. Yes, and if f was balanced, then there would be no coefficient in front of all zeros. So there is the probability that a result of measurement will be all zeros is equal to 0, because coefficient in front of it is 0. So, and the final answer is that after the measurements, if all the measurements was 0, then f is constant. If I get some non-zero element, then the function was balanced. And so this is how kind of the magic of quantum computing works. Yes, because even that theoretically the measurement, as Altan mentioned, yes, is a probabilistic story, yes, still, okay, and we don't know what would be the output if f is balanced, but it's for sure would not be all zero, yes? And what is actually more magic, yes, is the following, yes? So because, sorry for the sliding back, yes? So when I applied UF to this state, I kind of, in one cycle, in one operation, calculated f of k for all k. I didn't measure any of them, but there was in all of those were involved inside. Yes, so kind of in one step I calculated all of them. Okay, I got some linear combination of them and so on, and because of this I properly chose gates here, properly chose gates here. So this linear combination gave me something meaningful. Yes. And so then this is what I have. Yes. Few remarks. Yes. So that's I used n+1 qubits. I used 2 n+1 Adamar gates. Okay. I also used one NOT gate, which I didn't write. And I just used one quantum oracle. And after all of this, I was able to determine is this function constant or balanced. If we speak about classical algorithms, then, I mean, theoretically, yes, we need to measure a bit more than half of them. So something exponential, yes. And so it happens that, I mean, quantum computer might be more efficient for this problem, yes. Of course, I missed the idea how UF is implemented, yes. Actually, even that I told that operators and or, and it's not possible to implement them in quantum computers. At the same time, actually, there is a trick how you can implement any logical function inside quantum computer. Yes, it might just happen that it would ask to use external qubits. Yes, but I will describe this later. Yes, not today. Yes, so actually any f which you logically can compute, you can compute on a comparable time in quantum world. Yes, but might be you will need more acyla qubits. Yes, more external qubits. Okay, looking onto the time, yes, I think it's not a good time to start a new topic, yes, because it would be not in a very, how to say, good shape, yes, done. So that's then on Thursday, yes, I will speak about qubit. So I will go to systematic studies of gates, yes, so I will first go to few qubit gates, 1 qubit gate, 2 qubit gates, show some tricks, yes, for like which are correct. Yes, and at some moment I will already pass more to algorithms. Yes, and also, so I encourage all of you, yes, send to me, your considerations, same as like for a blog sphere. Altan for actually send me before, yes, so that's his considerations about blog sphere on a different style than explain. So Altan is good, yes. So, but I encourage all others also to send me your considerations, duvidas, yes. I'm not promise reply immediately, but still I somehow reacting on the questions in WhatsApp. You can send not only in a public group, you can send me directly. Yes, that's also fine. Yes, yeah. You can send by WhatsApp, by email. Yes, so how it is more good for you. Yes. To email, I would reply with more details. To WhatsApp, I will reply faster. Yes, so that's how to say. But don't expect me that for the message in WhatsApp, I will send you a long reply with illustrations. Yes, but for email, no, I can do that. Yes, so sometimes I have some illustrations well prepared. Okay, so till Thursday, yes. And now the how to say second, I will repeat this class for those who are interested in Portuguese. Yes, so please stay those who are interested.